All right, we have a mixture problem here, which is going to end up being a linear system type of application problem. So let's read this one. A popular fruit drink is made by mixing fruit juices. Such a mixture with 25% juice is to be mixed with another mixture that is 10% juice to get 15 liters of a mixture that is 12% juice. How much of each should be used? And they also give us this little table here to kind of help us set up our variables and think through this problem. So this is given to us. So if you look here, there's two types of juice. The first one has 25% juice, and we don't know how many liters of this juice that we're going to use. But however many liters we use or think of, the amount of pure juice would just be to multiply those together. So if I had 4 liters of this first type of juice, I multiplied 4 times 0.25, that would be 1. I would have 1 liter of pure juice in there. Same thing with the second one is we have 10% juice, and we don't know how many liters we're talking about or will be using in this problem, so we're going to call that y. So we're kind of scaffolded here to meant to use this chart as a guide to fill it in, right? So if you look at the second column, if we have 10% juice and we have y liters of it, well then how much pure juice of that would we have? Well, that would be 0.1 y. And then we're combining these things to make another mixture that is 12% juice. If you look at this problem, we already know we want to have 15 liters of a mixture that is 12% juice. So we know how many liters we want of this 12% mixture. We want 15. So we know that this is going to be 15 here. That's what our end result is going to be. And how much pure juice is going to be in this last mixture? Well, we could just multiply 15 times 0.12, and that gives us 1.8 liters of pure juice. Now, the last sentence here says how much, right? Oop, wrong button. How much of each should be used, right? How much of each should be used? How much of each of this first mixture and second mixture that we're going to use and combine should we use to make this last product right here, which is going to be 15 liters, and it's going to have 1.8 liters of pure juice, which is a 12% ratio there. So we're trying to find x and y here. So just a little visual here. Sometimes I like to just draw a visual just so you can kind of make connections and think about it in your head. So let's kind of think of these two different mixtures, right? We have a first container here, which is our first row here. That is a 25% mixture, right? So it has 25% juice here. So this little bottle is, let's just say 25%. It has 25% juice. And then the second mixture has 10% juice. So this is like a 10% juice. And what we're going to do here is we're going to take these things, okay, and I'm going to dump some of this mixture in, and I'm going to take this, I'm going to dump some of this mixture in, and I'm going to dump it into and make this, and make this bigger mixture here. Let's just think of it as a big old fruit juice. And this mixture is going to be 15 liters. I know I'm going to pour 15 liters in here, and I know that this is going to hopefully contain 12% juice. That's what we want. So I'm going to take this, I'm going to dump some of this mixture in, and I'm going to dump some of this second mixture in, and it's going to fill up to the top. And once I fill it up to the top, I want my end result here, of course, to be filled to the top, so I'm going to have 15 liters. And I want to make sure that I only have exactly 12% juice, or 1.8 liters of pure juice in there. So I got to figure out, okay, well, how much of this should I pour in and how much of this should I pour in to make this end result as it should be, okay? So here's where we're going to create our linear systems, and we're going to create these equations that show us the constraints of the problem. So one way you could kind of look at these different columns, and you could say, well, if you look at this column over here, right, we know that the end result has to have 1.8 liters of pure juice, okay? So if we were to take 0.25 times x, that would be the amount of pure juice in this first mixture, right? So again, if I used, let's say x was 4, if I used 4 liters, if I dumped 4 liters of this first solution into the bin there, the amount of pure juice that I'm going to be pouring in there is going to be 0.25 times 4, which is one whole liter of pure juice. Okay, if x was 4. You know, if x was like, let's say 10, right, 0.25 times 10 would give me 2.5 liters of pure juice. And I know it's not going to be 10, right, because that would already be much more pure juice than what we need, which is 1.8. So the point here is that we don't know how much we should pour in there right now, okay? But we're going to take 0.25x, the amount of pure juice from that first container, and then we're going to say plus 0.1 times y, the number of pure juice from the second container, whatever that is, that has to equal 1.8. Okay, we know that to be true. That's what should happen. Now we have one equation. We have two variables, so there's no way to determine what those two variables are going to be for this problem unless we introduce another constraint or another equation. And we do have another constraint, because if you look at the second column here, right, we know that the total amount that we need is 15 liters, right? So we can use this column right here to say, well, I know that x plus y, the amount of just liters that I pour into the thing and from the first mixture and then from the second, has to equal 15. Those have to be true, okay? So this is kind of the hard part of the problem, is to think about the information that they give you and then set up a system of equations that can correctly model what the problem is telling us, okay? And here's a system of equations that would do that. Now we're just going to look at this system and just kind of abstract away all the details and just focus on the algebra. That's the whole point of modeling in math, is we just want to take equations, forget about the details of the problem for a second. I'm just going to solve this system and I'm going to get to my answer. I know that I have to find x and y to get my answer. So I'm just going to zone in here and just solve for x and y. Well, this is a linear system, so I can solve it through substitution or elimination, one of those two things. So you can kind of take your pick here. In the last video, I believe I used substitution, so I'm going to use elimination here. Okay, elimination means we're going to multiply one or both equations by a number so that when we add the equations, we can eliminate. So let's see here. I'm going to multiply this top equation. Let's just say I want these x's to match up. So if I multiplied it by 4, I know that my x term would be 1x. And I'm going to predict here, I really want it to be negative 1x here so that they're opposites. So therefore, when I add, it'll eliminate to 0. I'm actually going to choose to multiply everything by a negative 4 here. And I'm going to write this new equation below the second equation. So if we do that, this would become, this would be negative 1x plus now 4. So this would be negative 0.4y equals, and this would be negative 7.2 here. Now as you're going through this, just algebraically, for new algebra students, again, if you want to see that coefficient of your term, you can always throw in 1s there. Okay, so now I'm really looking at this new an improved set of equations that is set up for elimination. I'm going to go ahead and eliminate by adding these two equations together and combining the columns or the like terms. And so 1x plus negative 1x, well, that's going to go away. Then I add my y's. I'm going to get 0.6 y. And then equals 15 plus negative 7.2. That's going to be 7.8. And this is what we want to see here. Now I can solve this by dividing by 0.6. So 7.8 divided by 0.6. And what does that give us? Gives us 13. So this would be 13, and we got to an answer. Now that I went into math mode and I solved, let's think about, go back to the context of the problem and just think about what that means. Y here is 13, as you can see. Y represents the amount of liters of the second solution that we should use. So we should use 13 liters. Okay, basically this thing right here of this 10% mixture, we're going to use 13 liters of that. We're going to dump 13 in. So we'll say 13 liters of the, for lack of a better term, 10%, or let's say 10% mixture would be the first one. Okay, so that's part of our answer. We say, well, what about x? Well, just go back to one of our equations up here, right? We'll go back to this one right here. We know that x plus y is 15. We know that we have to make 15 liters. So if I pour 13 from this second solution, well, that means the first solution I have to use only 2 liters. Because x plus y, if you do the algebra, x plus y equals 15. We know that y is 13, so I could plug in 13 there. Well, what does x have to be? Of course, it has to be 2. So then we would say, well, x equals 2, and this would represent 2 liters of the first solution, or we'll just say the 25% mixture here. So those, I go back to my problem and maybe just think over, maybe check my work here, look at what was being asked, which is how much of each should be used, how much of each mixture should be used. That's what my x and y were, and that's what I'm giving here as my answer. 2 liters should be used of the first bottle, and then 13 liters of the 10% mixture should be used. And that's going to give us 15 liters of 12% juice here. Awesome.